Hey everyone, welcome to the video notes on geometric sequence and series. I am recording live from my house during this quarantine. Such a crazy time in history, and yet at the same time, it's also kind of boring. But hopefully you get bored enough that you maybe take a look at this with me. Because this is from my home, I'm a little bit limited in the technology that I have access to, so it's going to be a little bit different, but hopefully you can follow along. And of course, email me if you have any questions, and I'll get back to you as quick as I can. So hopefully you have viewed the video on arithmetic sequences and series. Geometric is kind of the same thing, except instead of having a common difference where we add or subtract a common number, now we're going to multiply by a common number called the common ratio. We're going to represent it with the letter R. So a geometric sequence is like an arithmetic sequence. It's just a list of numbers that are a pattern. And a geometric series is where we find the sum of a list of numbers that are in a pattern. Okay, so identifying if we have a geometric sequence. So in this case, our list of numbers is 5, 15, 45, and 135. In each case, we're multiplying by a common factor or ratio of 3. So yes, this would be a geometric sequence where the common ratio is 3. In the second example, our numbers are 15, 30, 45, and 60. In this case, we are not multiplying by the same number, we're adding by the same number, so this would be an arithmetic sequence, where the common difference is 15. Okay, so in number 2, they're asking us to take the sequence from the problem before, and to complete it up until the 10th term, and explain how we could find the 10th term if we were given the 9th term. So to list them all out, I just continuously multiply each term by 3, which we said was the common ratio, until I have 10 terms. So I end up with 98,415 for a sub 10. If I knew a sub 9, which I did, finding them one at a time, then all I need to do is multiply that 9th term by 3 to get the next term in the sequence. And that's what we do every single time to get the next term in the sequence. This is also known as the recursive formula. The recursive formula is what you do to find the next term of your sequence. So basically, it's just multiplying by your R value, your common ratio. In number 3, it's kind of just like number 1. Is it arithmetic, geometric, or neither? And so in this case, if we examine our numbers, we're multiplying by -4 every time. So that is a geometric sequence because we're multiplying every time by a common number. And in number 4, we are adding by a common difference. So that's an arithmetic sequence. Okay, here are your formulas for geometric sequences. The recursive formula, as we said before, is to take the previous term and multiply it by the common ratio. But the one that you'll use more often is the explicit formula. And please make sure there is a typo on the notes that I didn't catch until I started going over the notes. To find any term of a geometric sequence, we're going to take the first term, not a sub n minus 1. A sub 1 is what this should read. Multiply it by the common ratio raised to the n minus 1 power. So again, it should read a sub n equals a sub 1 times r to the n minus 1 power. So we're going to apply that to this word problem right here. Suppose you want a reduced copy of a photograph. The actual length of the photograph is 10 inches. The smallest size the copier can make is 64% of the original, and we're being asked to find the length of the photograph after 5 reductions at 64%. So our very first measurement, our a sub 1, is 10 inches. That's the size with 0 reductions. So if we reduce it 5 times after that, what we need to find is a sub 6, actually, or our n is 6 in this case. Even though we're reducing it 5 times, our first term is from 0 reductions. So we actually have to find the sixth term in the sequence. Our common ratio would be 0.64 or 64% of the original, meaning we're getting smaller and smaller each time. So as I plug these numbers into the explicit formula right here, I'm trying to find a sub 6. So I'm going to multiply that times a sub 1, which is 10, times my r value, which was 0.64, to the n minus 1 power, or I'm basically reducing it 5 times, which gives me, when I plug that into my calculator, 1.07 inches when I round it. Okay, this is again just using the explicit formula. Find your first time, find your r value, and find your n, or the number of the term that you are looking to find. In this case, they're asking us to find the 19th term. So we're just going to plug it into this formula again. And we get a big number, thousands, millions. It's 4,261,625,379. And it makes sense that it should be a big number. We're multiplying by 3 every single time. So when we do that 19 times, we are going to end up with a very massive number. In letter B, we're doing the same thing. This time we're subtracting. So this is an arithmetic sequence. So to find the 19th term, I'm going to use the explicit formula for arithmetic sequences, which is given here. You can refer back to those notes as well. So again, our a sub 1 is our first term, or 20. Our common difference is -3 because we're going down each time. And again, we're finding the 19th term in that sequence. So when I plug this in, I end up with -34. Okay, so here we're using geometric means. The geometric mean is the same thing as the arithmetic mean, except we are, again, using multiplication instead of addition. So to find the geometric mean of two numbers, we're going to multiply them and take the square root. We can use them to find the missing term of a geometric sequence. And really, anytime we're missing any odd number of terms, we could always use a geometric mean to find that. So the geometric mean of 3 and 27 is 9, or in other words, we are multiplying by 3. Our common ratio is 3. And so 3 times 3 is 9, 9 times 3 is 27, so it fits our pattern. Like I said, to find a missing term, we just use the geometric mean. But I said we could also use the geometric mean if we're missing any odd number of terms. So what I mean by that is if we look at number 2, we're missing 3 terms, we would find the geometric mean of our first and our last term to find the middle term right in here. So that we're doing the exact same thing as we did here. So the middle term is 16. And then what we'll do is we'll just use now the first and the middle term to find the geometric mean of the second term, and we'll do the same thing with 16 and 64 to find the geometric mean of to find the fourth term. The other thing you could do is once you know these two terms, you can just use the pattern to continue to find this term right here. So once you see, okay, this term's going to be 8, and this term we found was already 16, we can see that we're multiplying by 2 every time. So I can just take my 16, multiply it by 2 to get my 32. But again, the work is here. I just use the geometric mean twice. The first time to find the middle term, and then once more to find my second and my fourth terms. So what's a little bit different is if we are missing an even number of terms, then the geometric mean won't work because it'll find a number that is in between our two terms that we're looking for. So what we do here is we take the quotient of our first and our last term, and then we cube root that, because what we're doing is we're trying to figure out what number we multiply by 3 times to get these two missing numbers. So that's why we use the cube root. If we were finding like 4 missing terms, we use the 5th root because every single time we're having to multiply or divide by that number 5 times to get to the next or the last term. So anytime we're missing 2, 4, 6, 8, any even number of terms in a geometric sequence, we can't use the geometric mean. we're going to divide our first number by our last number to find the ratio of those terms, and then do one more than your missing number of terms, that root, to find the common ratio. So 54 divided by 2 gave me 27. I'm missing 2 terms, so I take the third root, or the cube root, and I get 3 for my common ratio. So I'm going to multiply by 3 every single time to get those 2 missing terms. So 2 times 3 gave me 6, 6 times 3 gave me 18, 18 times 3 will give me 54. And it will work even if you're getting smaller. Still divide your last term by your first term. That gave me 0.125. I'm again missing 2 terms, so I take my cube root of 0.125, which is 0.5 or 1/2. So every time I'm cutting my number in half, 500 becomes 250, 250 becomes 125, and 125 cut in half will become 62.5. So that's geometric sequences. Let's talk about geometric series, which is the same thing, except now we're just adding all of our terms in our sequence. Here's the formula for finding the sum of a finite geometric series. So again, we need our common ratio, and we want our first term and the number of terms in our sequences. So that's just found by counting up how many numbers you have. So our n is 6, our a sub 1 in this case is 3, and our common ratio is 2. I just plug it in, plug and chug. On the top I get negative 189, on the bottom I have negative 1, which simplifies to a sum of 189 in this case. Same thing here. My first term is negative 45. I have 5 terms in this series, and my common ratio is negative 3. I plug them all in, and I get negative 2,745. Okay. In this case, my a sub 1 is 1/3. I have 4 terms in my sequence. My common ratio is 1/3, or in other words, I'm dividing by 3 every single time. Plug that in, just be careful with your fractions, and it simplifies to 40 over 81. Okay, and now we're going to apply this to some real-world problems. So it says, in March, the Floyd family starts saving for a vacation in August. The Floyds expect the vacation to cost $1,375, and they start with $125. Each month, they plan to deposit 20% more than the previous month. Will they have enough money for their trip? So this is an example of a geometric series where they're adding up the amount of money that they have each month. So every time every month they're going to save 20% of what they have in that account. So they're taking the money that they have and they're saving 20% more. So this is confusing for a lot of people. Our R value is 1.2. So it's 1, meaning the amount of money that they have in the account already, and then they are adding to that another 20%. So the amount should increase every month, not decrease. So that's why our R value has to be greater than 1. They're going to do that 5 times, but the very first term, 125, is after they've added nothing to it. They haven't compounded anything. So that's why we're going to find the 6th term. It's very similar to the problem that we did with the geometric sequences. So we plug it in to this formula. S sub 6 is 125 times 1 minus the R value, 1.2 to the 6th power, over 1 minus R. Simplify that, and we find out that after 5 months of saving in August, they would end up with $1,241.24, which would not be enough if they think that their vacation is going to cost $1,375. They'll either need to start with more money or save more money. So in this second example, they're going to deposit 25% more each month, which makes our R value 1.25 to see if this would be enough money. And when we do the same thing using the same calculations, we can see that this would give them enough money. They would end up with more than the cost of the vacation at the end of it. Okay, so we have 2 types of geometric series. We have convergent series and we have divergent. Convergent means that the R value, the absolute value of it, so meaning regardless of its sign, is less than 1. So the numbers are getting closer and closer and closer to the